the last section of moment of inertia. We're introducing some new quantities and we're introducing some new notation as well. Now, it's a different method to complete the same type of questions that we dealt with previously. So questions where there's rotational kinetic energy and linear kinetic energy, we're going to look at it slightly differently. We're not going to look at it in terms of energy, but in terms of force and rotation. So force and torque, essentially, or force and moments. But before we get onto that, we need to have some notation. And it makes things a lot easier for me if you have this notation. So first of all, velocity is the derivative of displacement, v being velocity, s being displacement. So ds dt is when you differentiate the displacement with respect to time, and that gives you the velocity. That's the first thing. On the right hand side then, on the top line, when you differentiate something with respect to time, you can write that thing with a dot over it. So ds dt is the same as s dot. So s dot is the derivative of s with respect to time. In the second line, we have acceleration. Acceleration is dv dt, so it's the rate of change of velocity with respect to time. Or it's the second derivative of displacement with respect to time, so d2s dt squared. So on the right hand side then, double dot, s double dot means we'll be differentiating s twice with respect to time, meaning it's the second derivative. And I suppose you could also say the acceleration is v dot, so dv dt as well. So that's the first part. If you see a dot over something, it's a derivative with respect to time. If you see two dots over it, it's the second derivative with respect to time. Okay, second thing, the idea of angular momentum. So we know linear momentum is mass by velocity. Mass is how difficult it is to move an object, and velocity is how quickly it's going. Well, angular velocity is defined in a similar way. Moment of inertia, remember the I value, is how difficult it is to change the rotational speed of a body. And because it's rotating, we'll have a rotational or an angular velocity there, omega. So it's analogous to linear momentum, which is m by v, but it's just in a rotational fashion. Now, if we were to get the derivative of the angular momentum, so with respect to time, so if we say angular momentum is p, for example, dp dt, we then get the momentum of the right-hand side as well. Now, w is already theta over t, so w is already theta dot, and when we differentiate that a second time with respect to time, it becomes theta double dot. So torque can be looked at as the moment of inertia multiplied by the angular acceleration. So theta double dot is d2 theta dt squared. It's like an angular acceleration. It's how much faster the particle starts to rotate every second. Okay, so that's the first one, the torque. All right, we'll be using that later. And the second thing we're going to look at looks a little bit more complicated. So if we look at the top part there, we have s is equal to r theta. And that comes from the fact that the angle in radians is the arc length divided by the radius. Theta is s over r. You would have come across that in maths, physics, and I would have mentioned it when we did circular motion also. Well, if you differentiate both sides, well, ds dt is the velocity. It's also s dot. And that's equal to r times d theta dt. So if we look to the right then, we have v is equal to rw. W or omega being d theta dt. And then writing that in terms of the notation I put on the previous slide, v is s dot and omega is theta dot. So another way of writing that is ds dt is equal to r times d theta dt. All right, I'm going to go back to the v is equal to rw bit though, and we're going to differentiate once more. So if we differentiate the left-hand side, we get a, and if we differentiate the right-hand side, we get the derivative of w with respect to t, which is the same as, if we look just below v is equal to rw, the second derivative of the displacement is the acceleration, and the second derivative of the angle is the angular acceleration. So from that simple formula, s is equal to r theta, we now have s double dot is equal to r theta double dot. And I've explained the terms in the bottom right corner there as well. S double dot is the acceleration, theta double dot is the rotational acceleration. Now, that's the second formula we're going to use. There's a third one, which is F net is equal to ma, that you've come across already. And the way I set up these questions is I look at what happens linearly and apply F net is equal to ma to each individual particle. I look at the rotational body, and I have a look at the moment, or the torque, that's equal to I theta double dot. And then to link those two equations, I use the one down at the end there. S double dot is equal to R theta double dot. So 3 equations, the one on the bottom will link the other 2. Okay, so what types of questions are we looking at? Well, we're looking at the hoop or the disc rolling down a plane, that would be A. We're looking at pulleys, where the pulley has a moment of inertia, and if it rotates clockwise like that, the downwards force on the right would be greater than the downwards force on the left. In other words, the moment caused by the right hand tension is greater than the moment caused by the left hand tension. And in C, what would happen here is, because of the weight, the circular object, the disc, would rotate clockwise but also fall, and the tension actually causes it to fall because the tension is a moment. It's a force at a distance from the turning point being the center of the circle. And actually the turning point in all 3 cases is the center of the circle. That means we'd be looking at the moment of inertia through the center of the circle in each case. Okay, so like I said, there are 3 things that we're going to do with each of these questions. And this method can replace the kinetic energy and potential energy method we used previously with similar questions. The only thing is, part C is easier to do via this method. It's much more difficult to do with the energy method. So the first thing you'll see me doing, I look at objects traveling linearly. I'll use F net is equal to ma, and I'll be replacing A with the displacement double dot, so S double dot, the second derivative of the displacement. We'll be looking at objects rotating. So T is the torque. I'm actually using it for the total moment here, so force by perpendicular distance, is equal to the moment of inertia by that angular acceleration component there, theta double dot. And then when I have those 2 equations, I'm going to link the 2 with S is equal to R theta double dot. And usually what I do is I take the rotational object's formula, get R theta on it, R theta double dot on its own, and sub in S double dot instead of it. That means then I'll be left with 2 equations with forces and accelerations, and I can solve for whatever I need. So it just becomes almost like a connected particles question. Okay. Example 1. So we have a disk of mass m, radius a, rolls straight down a rough plane which is inclined at an angle alpha to the horizontal. The coefficient of friction is 1/3. Find the acceleration and what's the greatest possible value of alpha before slipping will occur. So the top 2 will be my force diagram, and the bottom one will relate to my rotation. So if we look at the forces acting on the circle or on the disk, the weight acts vertically down. That goes through the center point. The reaction acts at the point of contact between the disk and the inclined plane, and it acts perpendicular to the plane, so therefore through the center of the disk. Friction acts parallel to the plane or tangential to the disk, and it acts at the point of contact again between the disk and the plane. So what we need to do, just like any inclined plane question, we need to make sure that all of those forces are either parallel or perpendicular to the plane. So the resolved forces diagram has that done for us. Okay, the bottom diagram then, we have theta double dot showing there's an angular acceleration, and we can see that that angular acceleration causes a linear acceleration x double dot. And we know there's a relationship between those that we'll see in a moment. Okay, so let me make these diagrams a bit smaller, and here's what we're going to do. So the first section, we're looking at the linear motion. So if we look at where it says linear motion, beneath that, remember x double dot is equal to the acceleration, and I'm going to have those in my equations. So we look at F net is equal to ma parallel to the plane. So we have an mg sine alpha down the plane and F up the plane, and that's going to cause an acceleration down the plane. So we get mg sine alpha minus F equals ma, or mx double dot in my case. Perpendicular to the plane, no acceleration, so forces up and down relative to the plane are equal. So R is equal to mg cos alpha. Okay, now we look at the rotational motion. So just below the text where it says rotational motion, remember that theta double dot is the second derivative of the angle. So it's like angular acceleration. My formula in that case is the moment is equal to the moment of inertia by theta double dot. And the forces that I have in the top left-hand corner diagram are reaction, friction, and weight. So the reaction and the weight both act through the center point, so they have no turning effect. Only the friction has a turning effect. It's got a moment. If the turning point is the center of the disk, then F by A is the moment in that case. And that's what we have there below the script T representing torque. F by A is the moment. We know it's a disk, and the moment of inertia of a disk through its center is a half mr squared. The A is just the radius in this case. So we have our three equations, and then the last bit then is the thing that links them together is x double dot is r theta double dot, but sure, the radius is equal to the acceleration. Now what I'm going to do with the rotational motion formula is I'm going to cancel off the a's, and that will leave me with F is equal to a half m a theta double dot. And we know a theta double dot is equal to x double dot from the last equation. So that's the first line I get there. That means that the force is equal to a half times the mass by the acceleration, and that's the rotational equation. Now, if we follow the line across, if I sub that into the first equation, I get x double dot, which is the acceleration, is that value there. And then look, the next part is to get the tension. So, sorry, it's not to get the tension. The next part actually says if the object is on the point, is slipping, calculate the angle that will make that happen. So I go back to the formula that's got friction in it, which was the linear formula parallel to the plane. mg sine alpha minus f is equal to mx double dot. We know f is mu r, we're given mu, the r value we got from the second equation previously, and the x double dot we calculated from the previous part. Now you rearrange that, you divide everything by cos, and you get tan alpha is equal to 1, so alpha is equal to 45 degrees. That's example 1. Example 2. A disk of mass m and radius r has a light string wound around its circumference. One end of the string is attached to a point on the circumference, and the other is attached to a point on the ceiling above the disk so that it falls freely under gravity. The plane of the disk and the string remain vertical as the disk falls vertically from rest. Find the tension and the acceleration of the center of the disk. The diagram is there in the hand-drawn section below worked example WE 13.6. And there's a sentence there that says the plane of the disk and the string remain vertical as the disk falls. In other words, you can see the entirety of the flat surface of the disk there. As it falls, you will continue to see that the disk won't fall or tip forward or tip backwards. So go through the method again. Look at it linearly. Linearly, there's a weight and a tension. It's falling down, so you'll get mg minus t is equal to ma, where a we're writing as x double dot. Now look at it rotationally. The only rotational moment we have here is the tension, because the weight acts through the center. So we'll get t by the radius equals the moment of inertia. Again, it's a disk through the center, half mr squared by theta double dot. Cancel one of the r's on either side, and again, r theta double dot will be equal to x double dot. That's the link between the two formula. So I get t is equal to a half mx double dot. I have mg minus t is equal to mx double dot. I can sub in the t value that I get from the rotational section into the linear section and simplify it, and you get the two answers there. You should be able to do that yourself. If you have any doubts, please do it. Third example. A fixed pulley of mass m and radius r turns on a frictionless axis. Masses m and 4m hang from either ends over a light and extensible string which passes over the pulley. Show that the common acceleration is that. Okay, if you look at the diagram that we have, we can see that you have two tensions here, S and T. They're not equal, and the reason they're not equal is because the pulley has a moment of inertia, so in order for it to rotate anti-clockwise, the T must be greater than the S. Okay, so we treat this like a normal connected particles question, except for we have different tensions and we also have to take into consideration the rotation of the pulley. So look at it linearly first of all, and you get 4mg minus t is equal to 4ma, s minus mg is equal to ma, the a being x double dot again. That's for the two particles. Rotationally though, we have two forces trying to make it rotate in opposite directions. The bigger one is going to be the t because it will rotate counterclockwise. So its moment is t by r, which is the radius of the disk. Subtract off s by r, which is the moment of the other guy, to get the net moment counterclockwise, and that equals I theta double dot. The same thing as previous questions, one of the r's will cancel all the way across, and then r theta double dot, we can replace that with the link between the two equations. That will become x double dot. The double dots there are not visible, but I should end up with t minus s equals a half mx double dot. And then you'd solve the three equations. From what I can see, you could probably just add the three equations. The tensions would cancel, and you'd get x double dot is 6g over 11. Look, again, if you're not sure of it, you do this question. And here are two for you. Pause the video, do them, and that's your work today, lads.